order to solve the differential equation xy prime minus x plus 1 times y equals to 0 around x equals to 0. So for the most part, we will be solving differential equations mostly around x equals to 0. That is using essentially a Maclaurin series, not a Taylor. Taylor series, it's centered somewhere else. Okay, but of course, I'm going to show you how do we get the solution around another point. So number one, y. Okay, so y. Assume the solution y equals sigma n equals 0 to infinity c sub n x to the n y prime in this case sigma n equals 1 to infinity of n c sub n x to the n. And guys, I'm going to switch to the letter C rather than the letter A because most of the times my A's can look like nines or Q's. Also, from now on, every time we take the derivative of the series, we will shift the starting index from 0 to 1. Because what happens to the polynomial when we differentiate it? Well, the first term goes to 0, which is a constant. So now the first term should correspond to n equals to 1. That's not what I did in the previous example, but now I'm going to do it. Okay, so let's substitute this into the differential equation. That is, actually, let me rewrite the equation xy prime minus distribute minus xy minus y equals to 0. Okay, so this will be x times sigma n equals 1 to infinity of n c sub n x to the n minus 1 minus x times sigma n equals 0 to infinity of c sub n x to the n, and then minus another minus simply sigma n equals 0 to infinity of c sub n equals, c sub n x to the n equal to 0. Okay? Well, before getting to put together all the series into a single one, we should introduce this x into the series. Introduce this x into the series, all right? So do you guys agree that these x's right here have an invisible power of 1? And well, when we multiply the x's together, we add the exponents. So what is 1 plus n minus 1? Isn't that sigma n equals 0 to infinity of n c sub n x to the n, because 1 plus n minus 1, that's just n. Okay? Minus sigma n equals 0 to infinity. Oh, wait, no, this is still n equals to 1, starting at 1. And then that's c sub n x to the n plus 1, yn plus 1. We already had an n. We have a 1, x to the 1 plus n, that's n minus 1. And the third series remains the same, minus sigma n equals 0 to infinity of c sub n x to the n equals to 0. Okay, guys. Mostly our goal is to write all series have, well, we want to have like series in order to combine the series into a single one. That means having the same starting index and also the same power of 1. Okay, guys, well, let's focus on not power of 1, the power of x. Focus on the power of x. Identify the largest of them. Well, so here it seems like we want to write everything in terms of power n plus 1. Okay, but we have a little problem here. We have a 0 here. Well, actually, we can do that with the first series. Okay, for the first series, I can add 1, add 1, add 1, and then we can subtract 1. So with this, we would actually do two things. Number one, to have the n plus 1 power and to have the starting index at 0. All right? Okay, let me actually do one step at a time for this one. Oh, wait, no, maybe not. Maybe not. Let me actually talk about the third series. Okay, so guys, for the third series, we have a little problem. So, of course, we can add, subtract, however we want, but for our purposes, check. If I add 1 to the series here, then I would need to subtract 1 in the starting index. But do you see the problem? We cannot have a negative starting index because again, a power series is supposed to have power zeros and on, not negative exponents. That's something else, like I mentioned last time. That's complex analysis. Those are called Laurent series. Yes. So, what we're going to do, so we cannot have negative one. So what we're going to do here, well, so this is where we make wishes come true, all right? Didn't we wish our starting index were a 1? So if we subtract that 1, that becomes a 0, and we are still in we're not in any issues. So for this is what we're going to do. Expand, expand, n equals to 0, expand the term related to n equals to 0. And here, what did we do? Complete shifting. All right, we did a complete shifting here. So this will be sigma n equals 0 to infinity n plus 1 c sub n plus 1 x to the n plus 1. Okay, minus the second series remains the same, n equals 0 to infinity c sub n x to the n plus 1 minus, okay, let me open brackets for this. Okay, I'm going to expand the term for n equals to 0. That'll be c sub 0 x to the 0 plus sigma n equals, because I expanded the term for n equals to 0. When I write the series, now we're going to start it at 1, right? C sub n, x to the n, okay, equal to 0, all right? So now, okay, let me subtract these two, and well, this would be equal to c sub. Well, let me start over here. Sigma n equals 0 to infinity n plus 1 c sub n plus 1 x to the n plus 1 minus sigma n equals 0 to infinity c sub n x to the n plus 1 minus, okay, x to the 0, that's 1 times c sub 0, that's c sub 0, minus sigma n equals 1 to infinity of c sub n x to the n, okay, and let that be equal to 0. Now, did you see how we can add 1 to all the n's inside of the last series and subtract 1 to the starting index? That's going to take us to the power n plus 1 and to a starting index at 0. Okay, so let's subtract, add, add, right? That means a complete shift, complete shifting. All right. Okay, so let me do that. Okay, this term right here, guys, well, be careful. That negative C0 is not part of any of the series in sigma notation. It's an independent term. When we have something like that, we would like to write those at the very beginning. Negative C sub 0 plus sigma n equals 0 to infinity n plus 1 c sub n plus 1 x to the n plus 1 minus sigma n equals 0 to infinity of c sub n x to the n plus 1 minus sigma n equals 0 to infinity of c sub n plus 1 x to the n plus 1. And let that be equal to 0. Okay? So do we have like series finally? Do we have all the series with the same starting index and with the same power of x? Okay. So what do we do? Okay, let's compress everything into one series. So negative c sub 0 plus sigma n equals 0 to infinity of, I'm going to write n plus 1 c sub n plus 1 minus c sub n minus c sub n plus 1 times x to the n plus 1. What am I doing here? I'm factoring the x to the n plus 1 to the right, and I'm factoring the sigma notation to the left. Okay? And let that be equal to 0. Okay? So, guys, here is where we going to generate the coefficients, but unlike the example we did last time, we didn't have any term like outside of the series. So we just have the series, the same series as before. So this time, what are we going to do? Okay, so do you guys agree that this is a 0 plus x plus 0x rather plus 0x squared plus dot 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 plus 0 x to the n plus 0 x to the n plus 1 dot dot dot. Do you guys agree with that right hand side? It's all zeros, but I mean it's because of those are the coefficients of zero coefficient of x, zero coefficient of x squared, etc. Well, because this is a constant, isn't it? The constant equals the constant, all right? And the coefficient of x to the n plus 1 should be equal to the coefficient of x to the n plus 1. Actually, you don't have to write all those terms on the right hand side of the equation. I'm doing it this time just so you can see how are we equating the coefficient. In the later exercises, this is just going to go equal to whatever, equal to whatever. Okay, so here we're going to have the following. Number one, we're going to have the fact that negative c sub 0 isn't that equal to 0, which implies that c0 equals to 0. And this is key to when we generate these coefficients. So that's number one. Number two, the quantity highlighted with pink, that is n plus 1, c sub n plus 1 minus c sub n minus c sub n plus 1. Let that be equal to 0. Okay. So what are we going to do here? I'm going to distribute c sub n plus 1. C sub n plus 1 times n plus c sub n plus 1 minus c sub n minus c sub n plus 1. Let that be equal to 0. And while I'm doing this, because, boom, boom, we're going to cancel a couple of terms in our recurrence relation. Okay? So that's going to leave us with the following. N c sub n plus 1 minus c sub n. Let that be equal to 0. Again, we every time we reduce or we come up with this recurrence relation, we solve this equation, well, relation equation for the c with the largest subscript. In this case, c sub n plus 1. So that is n c sub n plus 1 equals to c sub n, which is c sub n plus 1 equals to c sub n over n. All right? And guys, we're ready to use this recurrence relation to generate some coefficient. All right? Here we go. Okay. Guys, my advice when we're doing something like this, do not omit any detail. Please write every single detail. Do not omit like, oh, this looks obvious. No, because this actually the details actually matter for these ones. All right. Okay. Here is the weird part of this particular example. So we're going to generate coefficients for different values of n. Where do we start? We always start with the n. That's the same as the starting index in the series. So we're going to start at n equals to 0. So substituting in in the recurrence relation, which actually let me highlight it. Let me highlight it for you. We're going to use this relation to get the coefficient. So c sub 0 plus 1, isn't that c sub 1? Okay, c sub 1 equals to c sub 0 divided by 0. Oh, wait. We have a little problem. Can we divide by 0? No. Also, what c sub 0 from before? Okay, this is good actually. 0 over 0. Why is this good? Where have you seen this 0 over 0 before? What is it? It's an indeterminate form. Yes, it's an indeterminate form. Okay, guys, check this out. This is indeterminate. What does that mean that this is indeterminate? Well, remember how when we get a general solution to a differential equation, we always get to a plus c or maybe a c times a function that is an arbitrary constant. Well, so that means c1 will be that arbitrary constant because at this point it's not determined what it is unless we have an initial condition. So don't freak out if you get to wait, no, that's no solution. Goodbye. We're done. Next one. No, 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 no. Check. Check what we're gonna do. Let's keep generating. N equals to 1. That'll be 1 plus 2. Is that c sub 2? That equals c sub 1 over 1, which is c sub 1. Okay? But actually, what is c sub 1? Okay? No, wait. So that's C sub 1. This means C sub 2 equals to C sub 1, okay? Which at the same time, we already know C sub 1 will be our undetermined coefficient, if you will, okay? So what about n equals to 2? Okay, n equals to 2, that'll be C sub 3 using the relation here. That is C sub 2 over 2, which is, what is C sub 2 actually? So that's 1/2 c sub 2, which is c sub 1, okay? And then what's next? N equals to 3. That'll be c sub 4 equals to c sub 3 over 3, which is 1/3. What is c sub 3? Isn't that a 1/2 c sub 2? Okay? Are you guys following me here with how I'm substituting? So this is what we call a recurrence relation because it depends on the previous term somehow, on the previous, and then on the previous, and then on the previous. Okay. So what about for n equals to 4? Let's just do a couple more. That'll be c sub 5 equals to c sub 4 over 4, which is 1/4 c sub 4. But what is c sub 4? Isn't that a 1/3? Times 1/2 times c sub 2. Wait, no, this is actually c sub 1, right? Not c sub 2, c sub 1. All right? And guys, I believe this you should be able to see a pattern, right? Did you see the factorials in the denominator, but with a little twist? Hold on, not yet. Let me do one more. C sub 6 equals to c sub 5 over 5. That is 1 over 5 times, boom, all this madness. 1 over 4 times 1 over 3 times 1 over 2, c sub 1. Okay. Okay, guys. Yes, we see the factorials there. However, with a little twist. Would you agree that the next c sub 7 would be, I mean, I'm not going to do the whole thing. It's just 1 over 6 times 5 times, wait. 1 over 5, 1 over 4, 1 over 3, 1 over 2, c sub 1. Do you guys agree with this? Okay, but did you notice how far the factorial goes? It goes as far. Okay, do you see this 6? Isn't that 1 unit less than the corresponding coefficient? So inductively, we could we could say c sub n equals to 1 over n minus 1 factorial c sub 1. Okay, so that is going to be our c sub 1. Okay, so guys, we may go back to the proposed solution. Remember y equals to sigma n equals to 0 to infinity of c sub n x to the n. Okay, let's go back to that. So let me continue here. So y, which is equal to sigma n equals 0 to infinity c sub n x to the n equals to sigma n equals 0 to infinity. What's our c sub n? 1 over n minus 1 factorial. Okay? C sub n x to the n. And that's the solution. Not yet. Do you see the problem here? No, this is not yet the solution. It can't be. Yes, no, we're in the right track though, but there's a little plot twist here because, okay, think about n equals to 0, all right? What happens if you substitute n equals to 0, that is negative 1 factorial? The factorial is not defined for negative numbers, right? It's not. It's not defined. Um, so, but cannot calculate factorials for or of negatives. Right now, um, so what I'm gonna do is simply I will write y equals to simply shift the index, an incomplete shifting of the index, n equals to 1 infinity, okay, of n minus 1 factorial c sub n under 1 c sub n x to the n. And the reason why we can do this is because a, remember the c sub 0. What is c sub 0 equal to? Wasn't that equal to 0? So it doesn't matter, right? It doesn't matter if I just change the series to n equals to 1. This is one of the weird parts of the solutions by series. So with this, guess what? Even better. Okay, oh, actually this is c sub 1, not c sub n. Also c sub 1 because it was already in terms of c sub 1. Okay, I'm going to take that c sub 1, y equals c sub 1 sigma. And check this out. I'm gonna shift again with a complete shifting. N equals to 0 to infinity. Add 1 over here, n factorial, x to the n plus 1. All right, n to the n plus 1. And this would be C1 sigma n equals 0 to infinity x to the n times x over n factorial. The x is not part of the variables of the series. Take it out, which is c sub 1 x sigma n equals 0 to infinity of x to the n over n factorial, which is c sub 1 x. Oh, actually, this is the solution as a series, but this can be written as a function c sub 1 x e to the x. In some cases we may be able. In some other cases we may not be able to do so. Okay? Yes. All right. Solve the differential equation 2 minus x quantity times y prime minus y around, again, x equals to 0. Okay, again, assuming y equals to sigma n equals 0 to infinity, uh, c sub n x to the n, and y prime equals to sigma n equals 0 to infinity of c sub n x to the n minus 1. All right. Well, let's to the differential equation. First, I'm going to distribute the y prime, that is 2y prime minus xy prime minus y equal to 0. Okay? And let's just substitute the series, okay, and its derivative. So that is 2 times sigma n equals 0 to, oh, wait, n equals 1. Actually, I forgot to do the n equals to 1 to infinity n c sub n x to the n minus 1 minus x sigma n equals another 1 to infinity n c sub n x to the n minus 1 minus the original series. Okay? Well, here's where the fun begins. Put together all series into single one. Okay, yes, well, there's gonna be a little plot twist sort of here. Well, you'll see. So, number one, I'm going to introduce these two. I'm going to introduce this x right here, and I'm going to leave the third series alone. So, this will be sigma n equals 1 to infinity of n, oh, wait, 2n, c sub n, x to the n minus 1 minus sigma n equals 1 to infinity of n c sub n x to the, do you guys agree it's going to be x to the n only? Adding the powers, power of x equals to 1 plus n minus 1, that's just going to be n. And then minus c sub sigma n equals 0 to infinity c sub n x to the n equals to 0. What do we do here? Oh, that looks like a 6, not a 0. Let me change it to a 0. Okay. Again, look for the highest power of n. That's x to the n. All right? Do you agree with that? Okay. So, what about the series in the very middle, the second term? Okay. Yes, it has what's it called? It has an x to the n already. But do you see the starting index? It's 1, not 0. I mean, what we could do is subtract 1 and add 1 to the other, to all the indices inside the series, but that would jeopardize the power of x in the series. So we can't do that. All right. However, check. Do you guys agree that we could do an incomplete shifting? Incomplete shifting. Why we can do an incomplete shifting in this case? Because if I start at 0 here, what happens if I generate the term for n equals to 0? That'll be 0, c sub 0, x to the 0, which would be 0, isn't it? Remember when we discussed the two different shiftings, the incomplete and the complete, so we can do an incomplete shifting. And over here, oh, of course, we can do a complete shifting. Okay, so subtract 1, add 1, add 1, add 1. All right, and that'll do it, right? That'll do it. Guys, yes, I agree. This is one of the hardest parts of the problem. Again, it's like the mini boss. So, in the video game, so it's all right. So that'll be sigma n equals 0 to infinity 2 times n plus 1, c subscript n plus 1, x to the n plus 1 minus 1, that's x to the n, minus sigma n equals 0 to infinity. Everything else remains the same because incomplete shifting. Minus sigma n equals 0 to infinity, c sub n, x to the n equals to 0. And we're ready to combine this one into a single series. No terms had to be expanded this time. So I promise you guys, this is going to be a more straightforward one to do. You'll see. You're going to like this one. Okay? So, what is it? Oh, yes. Sigma bracket n equals 0 to infinity. That is 2 times n plus 1 c sub n plus 1, I'm factoring the sigma on the left, minus n c sub n minus c sub n, x to the n, equals to 0, right? So, in this case, again, I'm not going to write the terms like I did before on the right-hand side. Everything is a 0 on the right-hand side. You guys agree with that? Okay, so here we go. What do we do in this case? Let's set to n plus 1, okay, to n plus 1 c sub n plus 1 minus n c sub n minus c sub n equals to 0. Okay, let's solve the equation for the highest of the c. Okay, for the c with the highest subscript. In this case, c sub n plus 1. Let's move all these two terms to the right hand side to n plus 1, c sub n plus 1 equals to n c sub n minus c sub n. And then I'm going to divide both sides by 2n plus 1. So c sub n plus 1 equals, okay, 1, even better. So do you agree? Okay, wait, no, 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 this is a plus. Do you agree that in the numerator, or right here on the right-hand side, we can factor out c sub n? Okay, let's factor it out. Factor out c sub n. That is going to give us n plus 1. And at the same time, I'm going to divide by 2 times n plus 1. Guys, factor as much as you can when you get to recurrence relations, because that's going to help a lot when we generate all of these coefficients, all right? And in fact, do you see how this go away? So the calculations will be reduced big time here, guys. Okay, so let me actually continue maybe. Let me move this to this side right here. Okay. And this would be oh wait. C sub n plus 1 equals to C sub n over 2. All right? Yeah, that's a nicer one. Okay, so where do we start? We start at n equals the same starting index as the last step in the series in the differential equation. So we start at n equals to 0. That is C sub 0. Okay, let me highlight the recurrence relation so we can see where are we generating these coefficients. Okay, so C sub 0 plus 1 is that C sub 1 equals to C sub 0 over 2. Okay, I mean, there's not much to say here. N equals to 1. That is C sub 1 plus 1, which is C sub 2. That is C sub 1 divided by 2. But wait, this is 1/2 whatever C sub 1 is. But hey, what's C sub 1? Isn't that C sub 2? 1/2 C sub 2? I mean C sub 0, not C sub 2. C sub 0. Okay, let's do one more. Let's do one more. Actually, we don't need that many for this. So that'll be n equals to 2. That is C sub 3 equals to C sub 2 over 2. But what is C sub 2? So that is 1/2 whatever C sub 2 is, which is another half C sub 0. All right? Okay, guys, did you see the pattern? This is only powers of 2, isn't it? Okay, what is this then? So this looks a lot like maybe, I'm not gonna write the whole thing. This looks like uh C sub C sub 4 will be C sub 0 divided by 2 to the fourth power, isn't it? C sub 5 would be equal to C sub 0 divided by 2 to the fifth power. What about C sub n? Isn't that C sub 0, 2 to the n? Would you agree with this general rule? Okay, let's go back to the series. Let's go back to the series. So y equals to sigma n equals 0 to infinity C sub n x to the n. But what's C sub n? Okay, so sigma n equals 0 to infinity of C sub 0 over 2 to the n x to the n. And guys, this is the solution actually to as a series for real. This is a solution. Maybe just take out the constant C sub 0 sigma n equals 0 to infinity of x to the n over 2 to the n. Final answer. Wait a minute. We can actually write the related function, the function of x that's represented by the series. All right. So here we go. Do you guys agree? Okay, y equals to c sub 0 sigma n equals 0 to infinity. Okay, isn't that the same as saying x over 2 to the n? And does that kind of series look familiar for you? If so, what kind of series is that? Geometric, right? This is a geometric series with so c sub 0 sigma n equals 0 to infinity. What is it? Okay, u to the n, where u equals to x over 2. That is c sub 0, 1 over 1 minus u, where u equals x over 2. All right? And we're done. We're pretty much done. That is c sub 0, 1 over 1 minus x over 2, and multiply numerator and denominator by 2 to clear the complex fractions. That's going to give us c sub 0. Actually, I'm going to multiply c sub 0 times 1 times 2, which is, for now, 2 c sub 0. Okay? So that'll be 2 times 1, which is 2, and then divide out the x's minus x. But wait, 2 times c sub 0 by absorption, isn't that just still c sub 0? 2 minus x, which is the same as saying c sub 0 if you want x minus 2. Why is that? Because what if we multiply numerator and denominator by -1? to reverse the order of the terms in the denominator? Well, the multiplication in the numerator by c sub 0 with the negative 1, it's still going to be c sub 0 by absorption, isn't it? Okay. Okay. And yeah, that's the answer. All right. Okay. For the next example, solve the differential equation y double prime plus 4y prime equals 0 around x equals to 0. Guys, come on. We can solve that, even though we can solve that equation using the three cases. This is actually um, y equals c1 cosine 2x plus c2 sine 2x. Do you guys agree with that equation? I mean, with that solution? Just use, just using the higher order differential equations with constant coefficients. But guys, we're going to solve the same equation using power series. Okay, so here we go. All right, here we go. So we're going to set y equals to sigma n equals 0 to infinity. C sub n x to the n, the derivative y prime, that'll be sigma n equals 1 to infinity n c sub n x to the n minus 1. But this time we need the second derivative. We need the second derivative, that is y double prime sigma n equals 2. Okay, we add one starting index every time we compute one, the next derivative, n times n minus 1 c sub n x to the n minus 2. Okay? What do we need to substitute? The series representing the second derivative into the second derivative term. N equals 2 to infinity n times n minus 1. Okay? C sub n x to the n minus 2 plus 4 times sigma n equals 0 to infinity of c sub n x to the n equals to 0. So that's, we need to solve this equation. Huh? Um, we do. I mean, this is not, this actually will require complete shifting only. Do you guys agree with that? Because if we, okay, again, the highest power of x is n. Here we have an n plus 2, but we can easily add 2, add 2, add 2, and add 2. But if we subtract 2 to the starting index, are we going to have any problems with ending up with negative starting indices? Not in this case, so we're pretty much done, you know, at least with the mini boss, right? So sigma n equals 0 to infinity, n plus 1, n plus 2 rather, times n 2 minus 1, is that n plus 1? Okay, that's n plus 1. C sub n plus 2, x to the n plus 2 minus 2, is that simply to the n plus 4 times sigma n equals 0 to infinity of c sub n x to the n. Well, actually, let me introduce the 4 into the series. Okay, that'll be much better. That equals to 0, actually. And actually, we're ready to combine the two series together. All right? Sigma n equals 0 to infinity, bracket, n plus 2, n plus 1, c sub n plus 2, plus 4, c sub n, x to the n equals to 0. All right? Do we all agree with this so far? Are you guys following me up to this point? Okay. So we may go ahead and set the quantity inside of the series to come up with our recurrence relation. Let me do it here on the side actually. Okay. So that is n plus 2, n plus 1, c sub n plus 2 equals to negative 4 c sub n. All right. Well, I'm gonna solve for the constant C having the largest of the subscripts, that is C sub n plus 4. So that'll be, well, actually, yeah, minus C sub n plus 2, negative 4, C sub n over n plus 2, n plus 1. And this is our recurrence relationship, okay? So, a relation, actually. Let me actually highlight so you can relate to this when we generate our coefficients for the series. Okay? Actually, I'm gonna start just right below. Okay? I'm gonna start with n equals to 0. Why am I starting at n equals to 0? Because the last time we wrote the series in sigma notation, it had a starting index at n equals to 0. There will be cases, guys, in which the starting index may be at 1 or 2. So when we generate coefficients, we need to start at the exact same shift starting index. Okay, so n equals to 0. That'll be c sub 0 plus 2. Isn't that 2? Equals to negative 4 c sub 0 over 0 plus 2, 0 plus 1, which is equal to, do you guys agree, negative 4 c sub 0 divided by 0 plus 2, which is 2, 0 plus 1, which is 1, 2 times 1, is that a 2? And this is equal to, okay, so c sub 2 furthermore is negative 4 over 2 c sub 0, which even better. Okay, guys. Okay, check what we're going to do. I know what you might be thinking. Yes, divide by 4 divided by 2. Check. I know you're going to go like, why? You'll see later. You'll see later. I'm going to write this as a negative 2 squared over 2. Okay. Uh, 2 squared over 2 c sub 0. Okay. Actually, the reason to this is because these powers of 2 later on will play a big role when coming up with the general rule. Okay, so for n equals to 1, this will be c sub, what is 1 plus 2? Is that c sub 3 minus 4 times equals to negative 4 times c sub 1 over 1 plus 2, 1 plus 1. Okay, so that is negative 4. Okay, so negative 4, negative 4 times, negative 4 divided by 3 times 2, is that 6? Okay, is that 6? Or no, wait, what am I doing? Oh, no, no, you're right, okay. Actually, I'm going to write, instead of 6, check this out. I'm going to do simply 3 times 2. And at the same time, oh, this is c sub 1. And at the same time, I'm going to write negative 2 squared over 3 times 2. But what is c sub 1? From before, c sub 1, well, actually, we don't know what c sub 1 is, right? So that's going to be one of the undetermined coefficients, c sub 1. Okay, guys, to start to make sense out of this, keep in mind, we are solving a second order differential equation, which is supposed to have two unknown constants, right? One for every linearly independent solution. So those constants are going to be c sub 0 and c sub 1. So when we keep generating more of these coefficients, you will see this back and forth. C sub 0, C sub 1, C sub 0, C sub 1. Okay? What's next? So actually, I'm going to write this even better. How about as a 3 factorial? Much better, okay? Much better because I don't want to write too many products, okay? N equals to 2. Okay, n equals to 2. That'll be c sub 2 plus 2, which is 4, equals to negative 4 c sub 2 divided by 2 plus 2, 2 plus 1. Okay, what is that? Number 1, this would be negative 4, which is 2 to the second power, divided by 4 times 3. But what is c sub 2, guys? Isn't that c sub 2 back in terms of c sub 0? Okay, which will be negative 2 squared over 2. C sub 0, okay? What are we going to have this time? Okay, to begin with, guys, we're going to have a 2 to the fourth power Well, number one, negative times a negative equals to positive, okay? And then a 2 to the fourth power divided by, what's 4 times 3 times 2? Isn't that the same as 4 factorial? Okay, okay, we're good here. So n equals to 3. N equals to 3. That'll be C sub 3 plus 2, is that a 5, equals to negative 4 C sub 3 divided by 3 plus 2, 3 plus 1, okay? That is negative another 2 to the second power over, what is that? 5 times 4. Okay, but guys, what is C sub 3? Isn't that a coefficient in terms of C sub 1? Did you see again what I was talking about before? We're gonna go back and forth, bouncing back and forth between C sub 0 and C sub 1, C sub 0, C sub 1. Here you're actually seeing it, but actually careful with signs. Negative 2 squared over 3 factorial C sub 1. Okay, guys, what do we have so far? Don't we have another positive? 2 to the fourth power divided by, okay, what is 5 times 4 times 3 factorial? Do you guys agree that together they comprise the 5 factorial? Okay, great. 5 factorial C sub 1. All right. Next. Yeah, we're going to expand quite a few guys for this one, okay? So n equals to 4 up to n equals to 6. Not that many. But I mean, I think you guys are already maybe seeing the pattern here. So C sub 6 C sub 6 equals to negative 4 times C sub 4 divided by, what is that? 4 plus 2, 4 plus 1. Okay, this is another, okay, negative 2 squared divided by, is that a 6 times 5? Okay, but wait a minute. What is C sub 4? Isn't that another one in terms of C sub 0? Okay, so that'll be times 2 to the fourth over 4 factorial C sub 0. Okay, let's simplify this one. So that's negative 2 to the power 6 over, do you guys agree 6 times 5 times 4 factorial? Together they comprise the 6 factorial. Perfect. 6 factorial C sub 0. Okay, two more. N equals to, n equals to 5, right? That is C sub 5. Wait, no. What the hell? C sub 5 plus 2, no, that's C sub 7, isn't it? Equals to negative 4 C sub 5. 5 plus 2, 5 plus 1. Okay, so this is equal to another negative 2 to the second power over 7 times 6. But wait a minute, what's C sub 5? C sub 5, it's 2 to the fourth power over 5 factorial, but in terms of C sub 1, which is 2 to the, another negative 2 to the 6th power. Okay, wait, 2 to the 6 divided by, did you guys agree that 7 times 6 times 5 factorial together they comprise the 7 factorial? Okay, 7 factorial C sub 1. Okay, and then again C sub 0, C sub 1, C sub 0, C sub 1. Okay, and just one more, and I think we should do it with this. N equals to 6. C sub 8 equals to negative 4 C sub 6 over 6 plus 2, 6 plus 1. That'll be another negative 2 to the second power divided by 8 times 7. But wait a minute, what's C sub 6? Isn't that another negative, another negative 2 to the 6 over 6 factorial times C sub 0? Together they form, what is it? They form and oh, wait. They form a no, that's a positive this time. 2 to the eighth power divided by, okay, guys, do you agree that 8 times 7 times 6 factorial together they comprise the 8 factorial? Perfect. 8 factorial. C sub 0. Okay? C sub 0. All right. Oh, we're not done yet. We still have a long way to go. Okay. So, all right. Well, so I believe with this we have enough to write down our series. Okay. So again, just keep in mind that we had a series of the form y equals to sigma n equals 0 to infinity c sub n x to the n, which is what? C sub 0 plus c1x plus c2x squared plus c3x cubed plus c4 x to the fourth plus c5 x to the fifth plus c6 x to the sixth plus c7 x to the 7 plus c8 x to the eighth plus and so on and so forth, infinitely many terms, of course. All right. Well, the reason why I expanded quite a few of these generic terms, it's because we got quite, actually, we went all the way up to eight of them, right? Okay, so here we go. So let's substitute. So what is C sub zero? C sub zero, it's actually C sub zero, isn't it? There's nothing for C sub zero. That's the arbitrary constant as well as C sub one. Okay, so let me write y equals c sub 0 plus c sub 1x plus, okay, let me write in red at the top, c sub 2. Remember what was c sub 2? Okay, at the top, c sub 2, that was negative 2 squared over 2, okay? C sub 0. So I can write minus 2 squared over 2, c sub 0, and that's x squared, isn't it? What about, okay, that's C sub 2. What about C sub 3? Okay, C sub 3, um, C sub 3, negative 2 squared over 3 factorial, minus 2 squared over 3 factorial, C sub 1 this time, right? Yes, C sub 1. C sub 1, x cubed, okay? And then what about C sub 4? Let me write it in red at the top, C sub 4. And then what was C sub 4? Positive 2 to the 4 over 4 factorial plus 2 to the fourth c sub 0 back again, x to the fourth. What about c sub 5? Wasn't that, I believe c sub 5 is another positive, plus 2 to the fourth over 5 factorial c sub 1 x to the fifth. Okay? All we're doing is simply substituting into the original series. Okay? So plus C sub 6, okay, C sub 6. What was C sub 6 for us? Wasn't that C sub 6? Oh, actually, that was negative, isn't it? That's back to negative 2 to the 6th power over 6 factorial C sub 0 x to the 6. Okay, what else do we have? Uh, a minus. I'm going to continue down here. Another minus C sub 7. What is C sub 7? C sub 7. Oh, we have it here. All right, we have it in handy here, down here. So that is minus 2 to the 6 over 7 factorial C sub 1 x to the 7, and then plus C sub 8, which is 2 to the 8 over 8 factorial C sub 0 x to the 8 plus infinitely many terms. All right, guys, this is good enough. All right, but we're not done yet. Yeah, we're not done yet. We're getting there. We're almost there. Okay, so number one, do you guys observe that we have terms that have a c sub 0 and terms that have a c sub 1? So guys, this is what we're going to do. We're going to split this in two groups. One group with c sub zeros and another group of c sub 1s. Okay? So I'm going to write y equals to c sub 0 times, okay, c sub 0, that's 1. What's the next c sub 0? That's minus 2 squared over 2 x squared. Okay. And then what's the next c sub 0 plus 2 to the fourth over 4 factorial And then what's the next c sub 0? Minus 2 to the 6 over 6 factorial, uh, x to the 4th, and then minus x to the 6, all right? And well, another c sub 0, okay, the plus 2 to the 8 over 8 factorial, x to the 8. And then plus, or rather, it would be minus, I think, right? Minus dot dot dot, right? So that's the first group, factoring out the c sub 0. Now let's do the same with the c sub 1s. Okay? Let's do the same with the c sub 1s. So what do we get? I'm going to do it down here, okay? Let me actually use brackets instead of parentheses. So c sub 1, okay, x minus 2 squared over 3 factorial. Okay? Minus 3 factorial. X cubed, isn't it? And then minus, oh no, plus 2 to the 4th over 5 factorial, x to the 5th, and then another minus 2 to the 6th over 7 factorial, x to the 7, plus infinitely many terms. Do you guys agree so far? Okay, what do we have? What can we do? Okay, let's start let's working our way through the function representation. But there's gonna be, guys, a little twist in here. You'll see. There's kind of something weird here. Okay, number one. Do you guys agree the 2 squared times x squared, 2 to the 4 x to the 4, 2 to the 6 x to the 6, etc., they match with the power, right? Okay, so you guys might want to go to the back side of the page at this point if maybe you're already there. So that'll be y equals to c sub 0. So that'll be 1, okay, uh, 1 minus 2x quantity squared. Do you agree that 2 squared x squared equals to 2x squared? And also, guys, do you agree that the number 2 itself is the same as saying 2 factorial? It's just a fancy way to say 2. But we need the fancy way to say 2 because we want a pattern. And then plus 2 to the 4, x to the 4, that's the same as saying 2x quantity to the 4 power by laws of exponents. And well, we already have that 4 factorial. And then minus 2x to the 6 power over 6 factorial plus dot dot dot. I'm not gonna write this the eighth term, okay? I mean the eighth power, and then plus c1. Ooh, and here is where we're gonna have a little issue here. Okay, let me actually save some space. Okay, so plus, leave some space between the plus sign and the c sub 1. Okay, so what will that be? Okay, so number one, let me make this a little smaller maybe, and this will be x, okay, plus, oh, hold on, wait, 2 squared x to the third, all right, divided by, what is that, 3 factorial, plus, oh, wait, that's minus, and then plus 2 to the fourth over 2 to the 4 over 4, no, 5 factorial, x to the fifth power, minus 2 to the 6 over 7 factorial, x to the 7, plus dot dot dot. We have a little problem with the second expression, don't we? We don't have a match with the power of 2 and the power of x, so we can write it like the previous group. That looks like a little problem. Didn't we wish we had the same power, like an odd number, another odd number, another odd number? Again, here is where wishes come true. All right? Okay, guys, I'm going to multiply this by 2 like out of nowhere. Wait, why can I do that? I mean, this looks like, wait, for real? What the? Okay, so what was that? 2c1 equals to simply c1. In this direction, how did we call that? Absorption, right? Right? But what about the other way around? What's the opposite of absorption? Maybe rejection or uh generation, maybe? What word would you like for this? What is it? Repulsion, yes, repulsion, yes, repulsion, generation. And I mean, we're doing this repulsion, regeneration, or whatever, however, whatever word based on our need to make our wish come true and have the same power of choose, right? Now check this out. Let's keep going. Okay. Actually, the first group is ready, C sub zero times actually, well, I don't need brackets anymore. This would be sigma n equals 0 to infinity. Okay, this is an alternating series, isn't it? Negative 1 to the n, 2x to the n over 2n factorial plus, I still need to work here, c sub 1, 2x minus 2 cubed x cubed over 3 factorial, well, plus 2 to the fifth over 5 factorial, x to the fifth minus 2 to the seventh over 7 factorial, x to the 7 plus dot dot dot. All right? Okay, so now we can write this as a series, don't we? Essentially, I mean, not yet. I still need to, um, okay, y equals c sub 0, sigma n equals 0 to infinity, negative 1 to the n, 2 to the n, x to the n, over 2n factorial plus c sub 1 times 2x plus. Okay, do you guys agree this is 2x to the first over 1 factorial? Yeah. And then this is minus, actually not plus, minus 2x cubed over 3 factorial plus 2x to the fifth over 5 factorial minus 2x to the seventh over 7 factorial plus dot dot dot. Can we write this now like a series? But this time we no longer have even exponent. We have odd powers. Hold on. Hold on. This was supposed to be a 2n right here. And this is 2 to the 2n, x to the 2n. Okay? That's the first series. My bad. My bad. All right? Now, y equals to c sub 0, sigma n equals 0 to infinity of negative 1 to the n. So how about this is 2x to the 2n plus 1 over 2n plus, oh, wait, what the hell am I doing? 2n factorial. And I think I was looking ahead of the next one plus c1 bracket sigma. Well, no more brackets. We can go sigma n equals 0 to infinity of another negative 1 to the n. 2x, this time to the 2n plus 1 over 2n plus 1 factorial. All right? Let me distribute the powers here. Okay? Y equals to, what is this? Okay, so I did this. Okay, let me see sub 0, sigma n equals 0 to infinity, negative 1 to the n, 2 to the 2n again. I did it again, okay? X to the 2n over 2n factorial plus c1 sigma n equals 0 to infinity, negative 1 to the n, 2 to the 2n plus 1, x to the 2n plus 1 over 2n plus 1 factorial. This is our final answer using power series. But guys, can we identify what functions are there? I mean, I already spoiled it for you, didn't we, at the very beginning? Come on. Y equals to c1 cosine 2x plus c2 sine 2x. Yes, and that was that exercise here. All right. Okay, guys. So the next exercise will be a non-homogeneous differential equation. Well, the exercises we just did were homogeneous differential equations. How do we go about them? Well, pretty much the same. So the series for c sub n x to the n for the original function, the first derivative y prime sigma n equals 0 to infinity of n c sub n, oh wait, starts at 1. C sub n x to the n minus 1, but we also need the series for e to the x. E to the x equals sigma n equals 0 to infinity x to the n over n factorial. Okay? Mhm. All right, let's substitute everything into the equation. So sigma n equals 0 to infinity, what is that? N c sub n x to the n minus 1 minus the original series n equals 0 to infinity, c sub n x to the n equals x to the n, oh, wait, sigma n equals 0 to infinity of x to the n over n factorial. Okay? I mean, I don't think this is going to be. Oh, again, I keep forgetting to write the n equals to 1 for the lower bound, right? Okay, on the derivative. Okay, I'm gonna move the series. I'm going to move the series for the exponential from the right to the left. But at the same time, guys, let's start working with the combination of the series. I mean, the highest power is x to the n. The two series that have the highest power also have the starting index at 0. Do you guys agree with that? What about the derivative? Well, we can actually do a complete shifting by subtracting 1 to the starting index and adding 1 every inside of the series. Okay, that is sigma n equals 0 to infinity n plus 1 c sub n plus 1 x to the n minus sigma n equals 0 to infinity c sub n x to the n minus sigma n equals 0 to infinity x to the n over n factorial. And let that be equal to 0. And guys, this is great because we, at this point, we should be able to combine the series into a single one, can't we? Okay. All right, so that means sigma n equals 0 to infinity of bracket n plus 1 c sub n plus 1 minus c sub n minus 1 over n factorial times x to the n equals to 0. All right, starting index at 0, just set the expression equal to 0, n plus 1 c sub n plus 1 minus c sub n minus 1 over n minus n 1 over n factorial equals to 0. And again, we're going to solve for the c having the largest subscript. In this case, c sub n plus 1. So n plus 1, all right? N plus 1, actually, for the sake of spacing, let me move to the right. I mean, to the left. Okay, so that'll be n plus 1 c sub n plus 1 equals to c sub n plus 1 over n factorial, where c sub n plus 1 equals to c sub n plus 1 over n factorial, everything divided by n plus 1. So that is going to be our recurrence relation. Okay. All right. Well, how do we go about this one? Well, again, let's generate a couple of coefficients. So actually, I'm not going to generate that many for this one. Yes. Well, sometimes with just a few, it's good enough. But in some cases, you need a few more, especially when you're solving a higher order because you get coefficients for C1, for C2. So that's why we generated a total of 8 to give essentially 4 and 4 for each of the series. For this is back to our first order differential equation. We don't need that many. Um, okay, so C n equals to 0. That is C sub 0 plus 1 is that C sub 1 equals to C sub 0 plus 1 over 0 factorial divided by 0 plus 1. But what is that? Isn't that c sub 0 plus 1 over 1? Okay, which is simply c sub 0 plus 1. Do you guys agree with this? N equals to 1. C sub 2 equals to c sub 1 plus 1 over 1 factorial divided by 1 plus 1, which is, okay, this is c sub 0, okay, plus 1 over, what is that? 2, isn't it? Now, what is, wait, no, that's c sub 1. But what is c sub 1? Isn't that c sub 0 plus 1 plus another 1 over 2? And that equals c sub 2 equals to c sub 0 plus 2 divided by 2. Let me generate one more. For n equals to 2. For n equals to 2, we're going to c sub 3, okay? Okay, n equals, actually, you know what? Let me go all the way here now. For n equals to 2, that is c sub 4 equals to, wait, equals c sub 3. C sub 3, wait, c sub 2 plus 1 over 2 factorial. Yeah, I was looking here. So that's 2 plus 1. Okay, what's c sub 2? Okay, well, do you guys agree that c sub 2 is the same as saying c sub 0 plus 2 divided by 2? And then what is 1 over 2 factorial? Isn't that simply 1 over 2 over 3 over 3? Okay, okay, that division by 3, check this out. How do we handle this? This is the same as saying 1/3 times whatever we get from this. So do you guys agree same denominator? We can write this c sub 0 plus 2 plus 1, everything divided by 2. That is c sub 0 plus 3 divided by 3 times 2. Okay? But do you guys agree that this is the same as saying c sub 0 plus 3 over 3 factorial? Okay, do you guys agree with that? Okay, well, so n equals to 3. Okay, for n equals to 3, that'll be c sub 4 equals to c sub 3 plus 1 over 3 factorial divided by 3 plus 1. Okay, but what is that 3 plus 1? Isn't that 1/4 times, what is c sub 3? C sub 3 is this term right here, right? Isn't it? So that'll be, okay, c sub 3 plus 1 over, wait, c sub 0 plus 3 over 3 factorial, which is our c sub 3 here, plus another 1 over 3 factorial. Okay? Now, combining the two fractions together because they have the same denominator, we can 1 over 4. What is c sub 0 plus 3 plus 1? Is that c sub 0 plus 4 over 3 factorial? But guys, what is 4 times 3 factorial? Again, doesn't that comprise the 4 factorial? Okay? So c sub 0 plus 4 over 4 factorial. So I think we can already see a pattern, right? At this point, we can easily see. Okay? All right. So, much, yeah. Anyway, so y equals to sigma n equals 0 to infinity c sub n x to the n equals c sub 0 plus c1x plus c sub 2 x squared plus c sub 3 x cubed plus c sub 4 x to the fourth plus dot dot dot. All right, just substitute what we have. Okay, so c sub 0 is that c sub 0, right? So y equals c sub 0 plus, what is c sub 1? C sub 1, wasn't that c sub 1, c sub 0 plus 1? Okay, c sub 1 equals to c sub 0 plus 1. C sub 0 plus 1 x plus, what is c sub 2? C sub 2 is c sub 0, c sub 0 plus 2 over 2. But guys, I'm going to go fancy again. How about we write the number 2 as a 2 factorial? x squared. What about c sub 3? C sub 3, that is c sub 0 plus 3 over 3 factorial x cubed plus, what is that? C sub 4, which is c sub 4, I mean c sub 0 plus 4 over 4 factorial x to the fourth power plus dot dot dot. Okay? And I think, you know what, guys? I need to take my time for the remaining steps. It's not that much. I think I can do it in a couple minutes. No, let's do it. Let's do it. What the hell? What the hell? Okay, guys. Notice how we have terms x's multiplied by c sub zeros and x's multiplied by numbers without c's. Do you guys agree with that? Okay, so what I'm gonna do, let me. No, 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 no. Yeah, cliffhanger. Sorry about that.